Hello and welcome to this video on using the product property of radicals to simplify radical expressions. And this video is part one of two that I'm going to do with this title of using the product property to simplify radical expressions. All right, in this video I'm going to start off with a lot of wording. It's going to be kind of busy at first, just discussing, kind of refreshing your memory if you've seen a previous video of mine on the product property of radicals. So I'll refresh your memory as to what that is, and then also talk about a little bit about what it means to simplify a radical expression or simplify an nth root. And then go over some of the steps, and after all this busy talk, I'll do several examples where we're asked to simplify an expression involving a radical. Okay. So this first page, I've already written this out because again it would have taken me a while to write this out in the video. Don't want to waste too much time. So I'll just read this here to you. Top of the page I have a refresher of what is that product property for radicals. So it states the following: the nth root, right, a radical symbol with the index of n, the nth root of a times, right, product times the nth root of b will be equal to the nth root. So again, notice it's the nth root throughout, right? You don't have like a square root here and a cube root there. It's all the same root. Will be equal to the nth root, and the radicand over here is just simply the product of these two, right? So the radicand is a times b. It also goes in the other direction, right? If I see the nth root of a product of two factors, you can split them up. You can take the nth root of one factor and multiply it by the nth root of the other factor. So the nth root of ab is equal to the nth root of a times the nth root of b. But there's one caveat to this, and this is important. You can only use this property as long as the nth root of a and the nth root of b are real numbers. Okay, so off to the side, and I did this in my last video as well, but just to again refresh your memory a little bit. So if I had the square root of 2 and was multiplying that by the square root of 7, I can use the property there, right? These are both real. The square root of 2 is real, the square root of 7 is real because you have an even root, right? Even index 2, and the radicands are non-negative, 2 and 7. So here we could use the property for that example. But if I had, say, the square root of negative 2 times the square root of 7, right? Just one little change. The square root of negative 2, right, an even root of a negative number is not real. Right, is not a real number. That's been discussed in several videos now I've put up. So this is not real, okay, meaning that we could not use the property, right? Therefore we can't use the property in this case. Alright, so in the first example I could say the square root of 2 times the square root of 7 is equal to the square root of 2 times 7, or 14. And that's a perfectly true statement. This one, I can't use the property. I can't say that this is equal to the square root of negative 14. Right? I'm not even able to use the property because one of my radicals is not a real number. Alright, so don't even think about it. Right? But that's something you're going to have to keep track of, right? Only really when the roots are even, right? Square roots, fourth roots, because in those cases, remember the radicands, the numbers underneath the symbol had to be non-negative. If the roots are odd, right? Cube root, fifth root, it doesn't matter. Right? You can take an odd root of a positive number, a negative number, 0, and the result will be real. So really only focusing on, hey, do I have even roots or not? And if I have even roots, then I have to worry about what the radicand is, just to make sure my results are real. Alright, so this video is titled Simplifying, using the product property to simplify a radical expression. So what does that mean? Alright, so when I say simplifying a radical expression, right, something like the nth root of a radical expression with index n, right, so the nth root, will be considered simplified if the radicand, right, remember the radicand is the number underneath the root, right, inside the root. If the radicand does not contain any factors that are perfect nth powers, right? So if we're doing a square root, my radicand, in order to be considered simplified, the radicand can't have any factors that are perfect squares. If I'm doing a cube root, right, index of 3, the radicand can't have any factors that are perfect third powers or perfect cubes, and so on. All right, and then finally I'm going to get to the steps I'm going to be following, and I'll say these as we go through the examples later. I got 3 steps to simplifying a radical. Step 1, we're going to write each factor of the radicand as the product of 2 factors, one of which is a perfect nth power, right? So if I had a square root, I would break up my radicand, I would factor it so that I have one factor as a perfect square and the other factor is not. I'm going to try to do that. Or if I'm taking a cube root, I'm going to factor the radicand so that one factor is a perfect cube and the other factor is not. And again, if that's possible, I will do that. Step 2, this is where the product property will come in. I'm going to use the product property to write the radical, radicand, radical, as the product of 2 radicals, right? So we're going this way. We're going from right to left, and I'm going to take the product, the radical of a product, and write it as the product of 2 radicals, right? One of which contains perfect nth powers, right? So one of the radicals will have a perfect nth power in it, and the other one will not. And then lastly, we'll take the nth root of each perfect nth power. Now this is going to be harking back to another video I've made where we took the nth root of perfect nth powers before. You have to really, again, pay attention. Do you have an even root? Are you taking a square root, a fourth root, sixth root, etc.? Or do you have an odd root? So just hopefully you remember this from a previous video. If not, here it is again. Recall that if you're taking an even root, remember, when you see this symbol, when you see the radical symbol with an even number as the index, an even root, that symbol is telling you to give back the non-negative root. All right, because I said before, I mentioned in other videos, every positive real number has 2 square roots. One positive square root and one negative square root. Has 2 fourth roots, one positive fourth root, one negative fourth root. Basically every positive real number has 2 even roots, 2 even real roots, one positive and one negative. When you see this symbol with an even root, they want the non-negative one. So you don't just undo the powers. It's like most people take the nth root of a to the nth and just say, oh, nth root, nth power, they undo each other and just write a. Well, what if a is negative? Then you'll be giving me the negative root and not the non-negative one. So when it's an even root, you can undo them, sure, and just write a, but then to ensure that the result is indeed the non-negative root, we put absolute value symbols around it, right? So if n is even, the nth root of a perfect nth power is simply is going to be the absolute value of the base, the absolute value of a. And then if n is odd, it works kind of the way you want it. When n is odd, you can take the odd root of anything, and also the result can be positive or negative. It can be anything as well. Odd roots are nice. So when you take the nth root of a perfect nth power, a to the nth, when n is odd, you just undo those and you're left with the base a. Simple as that. But so really, again, as I mentioned in the beginning of the video, The most difficult situations happen when you have even roots. You really have to pay attention. Is my radicand non-negative? And additionally, is the final result non-negative? Am I giving back the non-negative root that that symbol is asking for? Okay? Alright, so I'm going to keep these steps to simplifying up here. Right, up at the top of the page, top of the screen, and then we're going to bring in my first example. So the first example I'm asked to, and then this is the same instruction for my first several examples, I'm asked to simplify each of the radical expressions. Alright, so here I have the square root of 48. And again, this symbol is asking me for the non-negative square root of 48. My final result should not be negative. Alright, so the index here is 2, right? This is the square root. Remember, technically I can put a 2 here and that wouldn't be wrong, but usually it's not written if it's 2 for square roots. So that means we're looking for perfect squares. Means we're looking for perfect squares. Alright, so 0 is a perfect square, but this is 48. 0 is not going to be a factor of any number we're looking at, really. But 0 is a perfect square still. I mean, but does 0 go into any number? No, it doesn't, right? So, 1 is a perfect square because it's 1 squared. 2 is a perfect. 4 is a perfect square because that's 2 squared. It can be written as 2 squared. 9 is a perfect square that can be written as 3 squared, and 16 is a perfect square, right? That can be written as 4 squared, right? Remember, any rational number that can be written as another rational to the second power is a perfect square. So 25, right? 36, and so on. Okay. And I know there's no variables in here, but I'm going to mention this right now. Basically, anything that can be written to the second power, any expression to the second power is a perfect square. So like if you had a variable x squared, or z squared, or x to the fourth, right? Basically, if your exponent is a multiple of 2, you have a perfect square, because x to the fourth is just x squared squared, right? If you remember that power to a power rule, where you would multiply these and get x to the fourth. So yeah, x to the sixth would be a perfect square. Z to the 8th, y to the 10th would all be perfect squares. And I'll just mention that right now. Really, if you see exponents that are multiples of 2, basically make up perfect squares. Exponents are multiples of 2. You'll have your perfect square. All right, because z to the 8th would be z to the 4th squared. Y to the 10th would be y to the 5th squared, right? You can use that power to a power rule to see how they are perfect squares. All right, so remember that first step was the following. The first step was write each factor of the radicand. So I'm going to take the radicand and write it as a product of two numbers, two factors, one of which is a perfect nth power, in this case a perfect square. So think of 48, and then what's the largest number of the perfect squares that goes into 48? Now I know you're thinking, hey, 4 goes into 48, right? 48 is 4 times 12. But 4 also goes into 12, right? I want to find the largest one. 16 actually goes into 48. 48, taking the radicand here, is 16 times 3. So here's your breakdown. That's step 1, right? Here's the breakdown where I take the radicand and I write it as a product of a perfect nth power, right? A perfect square, multiplied by something that is not a perfect square, right? 3 is not on this list. 3 is not a perfect square. Alright, so I'm going to do that. I'm going to rewrite this square root of 48 as the square root of, and then rewrite 48 as this product here as 16 times 3. Alright. And then step 2 is where I use the product property. Right? So here I have the square root of 16 times 3. I can break it up to the square root of 16 times the square root of 3, and that's fine because 16 and 3 are both non-negative, so they're both real numbers. You have the square roots of non-negatives, which are real. So using that product property, the square root of 16 times 3 is equal to the square root of 16 times the square root of 3. And then step 3, take the nth root of each perfect nth power. So that's this one here, right? Take the square root of 16. 16 was the perfect square. And what is the square root of 16? Again, the non-negative square root of 16, because I know negative 4 times negative 4 is 16, but the non-negative one is positive 4. So we have 4 times the square root of 3, which are usually just written like next to each other like this, without the dot. This is 4 times the square root of 3. And there you go. This is completely considered a simplified radical. Because the radicand now, right, here's the radical symbol. The radicand is 3. And, the only perfect square that goes into 3 is 1. But that's not interesting, right? But after that, 4, 9, 16, 25, those don't go into 3 evenly. Right. If 1 is the only perfect square that goes into your radicand, you're done. It is simplified. Great. And then we can double check. Right, if you don't believe it, all right, let's see if these numbers are actually the same. I'm going to pull out my calculator here. First when we started off with the square root of 48, which is 6.92820323 and so on, right? Some crazy decimal. It's irrational. And then let's see, is that equivalent to 4 times the square root of 3? Let's check. 4 times the square root of 3. And look at that, it is the same number, that 6.92820323 and so on. So this is correct. What we've done is correct, and again, it is simplified because the radical, the number underneath it, the radicand 3, has no other perfect squares that go into it evenly, no other factors that are perfect squares except 1, right? Again, the only 1 goes into anything, though. That's not interesting. Okay, now another way you could have done this that I've also seen, right, that is also just as valid, is, say you didn't see that 16 was a factor of 48 right away, Another way you could do this is also the following way. All right. So I'll say, or we could do the following. I have the square root of 48, and then let's factor the radicand completely. Right? Take it down to primes. Step 1. Right? Factor the radicand completely. Now you could do a little factor tree thing if you want. 48 is 2 times 2 because it's even. It's 2 times 24. Right, that's 48, and then 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. Right. And so when you factor 48 completely, right, take it down to all primes, which I've done here, right, there's 2, 2, 2, 2, and 3. 48 is 2 times 2 times 2 times 2. Another way to write that would be 2 to the 4th power times, and then, the only other prime is 3. And remember what I wrote up here. Basically, if you see any exponents that are multiples of 2, it's a perfect square, right? 2 to the 4th, see how that 4, that exponent is a multiple of 2. That is a perfect square. So I've done exactly what I did earlier when I wrote it. 2 to the 4th is 16, by the way, right? You've written it as 16 times 3 without even really seeing that, right? So I break that up. and then the same steps afterwards, right? So I'm not going to write it. So I factor the radicand completely. And then again, I break it up in the same way I did before, where we have our perfect square, 2 to the 4th, times, and then the non-perfect square, 3 to the 1st. And then use that the product property, the square root of 2 to the 4th times the square root of 3, and both of these are real since 2 to the 4th and 3 are both non-negative. And remember that little how is 2 to the 4th a perfect square? All right, 2 to the 4th is, using that power to a power rule, is 2 squared, right? Power to a power, I would multiply these, that'd be 2 to the 4th power. So if I want to write it as an actual square, right, with a power of 2, this square root of 2 to the 4th would be the square root of 2 squared, and then you have times, the square root of the non-perfect square, the square root of 3. And then this is my square root of something squared. So technically this would be the absolute value. Remember the even root of an nth power? The even nth root of an nth power would be the absolute value of the base. So it's technically the absolute value of 2 squared, but 2 squared is positive, so I don't need absolute value. So I get 2 squared, all right, the square root and the square power here undo each other. I get 2 squared, which is already non-negative, times the square root of 3. And, you should know what 2 squared is, right? That's 2 times 2. That's 4 times the square root of 3, which is exactly what I got, earlier. 4 times the square root of 3, 4 times the square root of 3. All right. So, honestly, I like doing this second way. All right. The first way I wrote was, from a textbook. I just took it out of some intermediate algebra text. I prefer this way, actually, where you factor the radicand completely. I'll say this is my preferred method, but I'll do both. Okay, I will do both for the next couple examples, and again, you really can decide which one you like better. All right, they both work out the same. All right, so let's look at the next example. So again, I'm asked to simplify this radical, and again, I'll punch it in a calculator at the end, see if we did it correctly. So I have 4 times, right, again, there's no plus or minus here, it's touching, so it's multiplication. 4 times, and then here's your radical. The cube root, right, notice the index is 3, right, so it's the cube root of 54. Alright, so I'm going to try to simplify the 4 is going to stay there the whole time. 4 times 4 times 4, there's going to be 4 there the whole time as a factor. What I'm trying to do is simplify this cube root. Now the index is 3, right, it's a cube root. So that means we're looking at perfect cubes. And I know there are some negative perfect cubes, but I'm not going to look at those. I'm just going to look at the non-negative ones this time. So 1 is a perfect cube, but again, that's not it. 1 goes into everything, right? Yeah, 1 goes into 54, but that doesn't help me, right? 1 is a perfect cube, right? Can be written to the 3rd power. 8 is a perfect cube, right? That's 2 cubed. Does 8 go into 54 evenly? No, it doesn't. Then 27 is a perfect cube, right? That's 3 to the 3rd power, and oh yeah, that's the one I want. 27 goes into 54. Well, let's see if there's any larger ones though. The next one though would be 64, right? Is 4 to the 3rd power, and that's too big, right? That's too big. It's bigger than 54. So yeah, the one I want is definitely 27 here. And as I did with the squares, right? Perfect cubes, you can have variables in them too, other factors like x cubed. X to the 6th would be a perfect cube because you can write that using that power to a power rule as x squared cubed, right? Is something to the 3rd power. X to the 9th is just x cubed, right? Using the power to a power rule, and so on. So if you have, if you have something to the, some multiple of 3, maybe the 15th power or something. If you notice that you have a base, you have a factor raised to a power that's a multiple of 3, then you know you have a perfect cube. A to the 15th, I could write as a to the 5th to the 3rd, right? A to the 5th cubed, using that power to a power rule. All right, so let's keep that in mind, and again, in my next video, it's going to come up as well, where we're going to see these, larger powers on variables and have to recognize when we have perfect squares or perfect cubes or perfect fourth powers, right, where the exponents have to be a multiple of 4 and so on. All right, so I'm going to do that first method where I break up 54 out. Here's the radicand, right, 54, and I'm going to factor it, where one factor is a perfect cube and the other factor is not. 54 is 27 times 2, right? That's 54. And one factor is a perfect cube, the 27, and 2 is not, right? I'm not seeing 2 on this list, right? All right, so let's do this. So this, 4 times the cube root of 54, that's 4 times the cube root of, and then the 54 I'm going to rewrite as 27 times 2. And then this cube root of 27 times 2, I can use that product property for radicals now and break it up. So this is still 4, right? Still got this 4 out here, times then the cube root of 27 times the cube root of 2. All right, and again, that was just using that product rule, product property for radicals. And then finally, we actually take the cube root of any perfect cube. And that was this one here, the 27. And what is the cube root of 27? Well, remember, 27 is 3 cubed. So this is really just the cube root of 3 cubed, leaving me with 3. So again, still have this 4 out here, times the cube root of 27 is 3 times the cube root of 2. And then we actually can multiply some of these factors, right? 2 of these are not in a root. So the two that are not in a root I can multiply in this product. 4 times 3 makes 12. Then we have times, a root. You don't multiply roots with non-roots, right? So 4 times 3 is 12, and then times, and again, so it'll be just touching, times the cube root of 2. And this is considered, a simplified expression, a simplified radical, because the radicand, right, the number underneath the radical, has no perfect cubes that go into it evenly except for 1, right, except for 1. All right, and let's test this out. I'll punch these in my calculator and see if they are indeed the same number. So we have 4 times, and then the cube root of 54. All right, that's giving me 15.1190526 and so on, right? So 15 point something. And hopefully if I did everything right, and I'm pretty sure I did, the value of this expression up here is exactly the same as the value of this expression here. 12 times the cube root of 2. And look at this, right? 15.1190526 and so on. They are indeed the same number. Great. Now, remember, I did it this other way too, right? Where you took 54, took the radicand, and factored it completely, right? Wrote it as primes. So, again, you could do this as 2 times 27, and then 27 is 3 times 9, and 9 is 3 times 3. You'd end up with 2 times 3 cubed, which is exactly the same as 2 times 27. 2 times 3 times 3 times 3. So it's the same thing as I'd have up there. So then we'd have, 4 times the cube root of 2 times 3 cubed. Or if you want to put the this is a perfect cube, right? It's got an exponent that's a multiple of 3 to the 3rd power. So I've got a perfect cube and then a non-perfect cube, right? 2 to the 1st. And then break this up. This would be 4 times the cube root of 2 times the cube root of 3 cubed, and then we have 4 times the cube root of 2, and then this cube root of a perfect cube, the cube root of 3 cubed, right, would just be the 3 again, right, just 3. And then you can rearrange these factors so that you multiply the ones without roots around them. You know, the 4 times the 3 would be a 12, and you know, then you'd have the other factor of the cube root of 2. So I end up with 12 times the cube root of 2 again. Alright. Okay. Alright, my next example has a variable in it. Alright, so you have to really be careful when there are variables. Especially when there are even roots, right? Again, another even root here. I have the square root of 200a squared, right? The radicand is 200a squared. All right. So what I'm going to do is, again, you know, you can do this the first way if you want. I'm going to do that whole breaking down the radicand completely. You know, so 200a squared, you know, 200, you know, if you take it off to the side, maybe do a tree if you want, right? That's 2 times 100. This is 2 times 50. This is 2 times 25, and that's 5 times 5, right? So here are my primes, you know, at the end of the branches here. So I have 2 to the third power and 5 squared. So it's 2 to the third times 5 squared times a squared. All right, that is the same thing as 200a squared. All right, so if anything has a power 2 or greater, you can peel off a square from that. Look at this, right? You know, every single one of these exponents is 2 or more. So what we can do here is peel off some squares, some perfect squares. Just peel off some factors so that the exponents are multiples of 2. All right. So let me show you what I mean. Like 2 cubed, right? 2 to the third power. And just think of what's the largest multiple of 2 that's less than 3, and that would be 2 itself. You can break this up into 2 squared, which is a perfect square, times 2 to the first, which is not. Right? And I'll just write out. I'm not going to write 2 to the first later, but you can write 2 to the first now. But you remember that first step from the first page. I'm going to go through each of these and write them as a perfect square times not a perfect square. So 2 cubed I can write as 2 squared, something to a power that's a multiple of 2, a perfect square, times 2 to the first, not a perfect square. The next factor is 5 squared. Well, that's already a perfect square, so I'm gonna actually write this stuff down. All right, so this is a perfect square. That's a perfect square. Sorry about the tininess of this. This is perfect square. This is not a perfect square. All right, 2 to the first. So the 5 squared I can't really break up anymore, into perfect square and not perfect square because it already is a perfect square. I guess you could say it's 5 squared times 1, but they're both perfect squares. And then a squared also has a power that's a multiple of 2, so it is also a perfect square. All right, so when we take our 200a squared and try to split it up into perfect squares and not perfect squares, the perfect squares are 2 squared times 5 squared times a squared. Right? I like to put the perfect squares first, and then the non-perfect square. Well, the only one of these that was not a perfect square was 2 to the first. So just times 2. This is exactly the same as this, right? It has the same factors. It has 3 2's, right? There's 2 2's there and a 2 there. It's got 2 5's. There's 2 5's, 5 5, and then a squared there. They're exactly the same. It's just, now it's split up to where I have my perfect squares things with powers that are multiples of 2, and then times, and then some factors that are not perfect squares. Okay, so let me do that. Alright, so I'm going to rewrite, instead of the square root of 200a squared, where I'm breaking this down to the perfect squares times the non-perfect squares. So you got the 2 squared times the 5 squared times the a squared times the 2. And now I'm going to use that product property. Now the product property, when you saw it, had the nth root of 2 things, a times b, but it can be extended to multiple factors if you wish. I could have a times b times c times d and take the nth root of each one of those if you want. Right? It can be extended to multiple factors, more than just 2 factors. Again, as long as all these are real though, right? As long as every single one of these, the nth root of a, nth root of b, nth root of c, nth root of d, and so on, as long as these are real numbers though, they gotta be real, can't be non-real numbers, can't be even roots of negatives. Alright, so I've written them, I've broken it up into my perfect squares times my non-perfect square, and then I'm going to use this product property to split them up. So this is the square root of 2 squared times the square root of the next factor, the 5 squared, times the square root of the next perfect square, a squared. And those are all my perfect squares, and then times the square root of the non-perfect square, 2. And then finally, comes the, now that I've split it up using the product property, take the square root of every perfect square. The square root of 2 squared would be, the absolute value of 2. Remember technically that? Going way back to, remember the square root of an even root of an even nth power of an nth root of an nth power is going to be the absolute value of a, the absolute value of the base. So this is technically the absolute value of 2, but we know what that is. The absolute value of 2 is 2 times the square root of 5 squared is, again, technically the absolute value of 5, but that is also a known value. The absolute value of 5 is 5 times, here's where we got to pay attention, it's a variable. The square root of a squared is not just a. This is wrong. Because what if a is negative, right? When you see the even roots, they're asking the even root symbol, square root, fourth root, you want the final result. The final result needs to be non-negative. So the square root of a squared is not a, it is the absolute value of a. Notice the absolute value symbols around that now. And then times the square root of 2, right? Which is that's the non-perfect square. Alright, and then we got some numbers that aren't in roots that we can multiply here. So this is 2 times 5 we know is 10. So 10 times the absolute value of a. Right, and again they're just touching, so it's multiplication. And then that stuff times the square root of 2, and again just touching, so it implies multiplication. And there you go. This expression should be equivalent to the original one. Alright, and let's test it out. Alright, let's try some value for a. Now you can, because this is a squared up here, you can plug in whatever you want. As long as the radicand is non-negative, a squared, when you square a number, any real number, it's going to be non-negative. So you can plug in anything you want for a. Alright, so I'm actually going to do that. Let's plug in a negative number for a and see if those expressions are equal. So back in the original expression, I have the square root, let me clear this stuff, I have the square root of 200 times, and then what I'm going to replace a with? I'll replace a with, say, negative 5. Negative 5. And then that's being squared, right? So there's the square root of 200a squared, where I'm replacing a with the quantity negative 5 there. Alright, so you see what we're getting is, so this crazy number 70.71067812. Da, da, da. All right, so if this is truly equal to what I've stated down here, then let me replace a with -5 down here and see that I get the same thing. So about 10 times. Now I can put in absolute value symbols, right? There is an absolute value symbol thing in my calculator. But if you want, you'd be like, hey, what is the absolute value of -5? Remember, that's +5, right? It's got to be a non-negative number when you take these even roots. But I'll put it in. All right, there's the absolute value of -5 there. I just hit the math button, went over the number. This is TA84, right? So 10 times the absolute value of a, which again I'm replacing a with -5, and then times the square root of 2, and hopefully I'm getting the same exact number as earlier, because these expressions should be equal no matter what a is. And look at that, it is 70.71067812 and so on. And try it out with some other numbers. Try out with calculators. Plug in any value for a up here, that same value for a down here, and the values of the expressions should be the same. They won't always be this 70 something. There'll be something else depending on what you plug in for a, but they should have the same value. Great. Okay, so again, be careful with even roots and variables and stuff. And I'm going to do much more of that in my next video, part 2 of this. All right, my next example. I got just a few more. Here we're taking the 4th root. Notice the index is 4, right? The 4th root of 40. All right, so I'm going to do that thing where I break down 40 completely. Now 40 is 2 times 20. 20 is 2 times 10. 10 is 2 times 5, and there's 2, 2, 2, 5, all the primes. That's 2 to the 3rd power times 5 to the to the 1st power. 8 times 5 is 40. Now look at these exponents. There's an exponent of 1 and 3. None of the exponents are 4 or greater. Right, the index is 4, so I'm looking for perfect 4th powers, things that can be written to the 4th power. None of these exponents are 4 or greater. So that means I can't break it up like I did the last example. I can't break this up into perfect 4th powers and non-perfect 4th powers. This is every single factor here. 2 to the 3rd and 5 are not perfect 4th powers, right? So this tells me, since none of these exponents are 4 or greater, that means that there is no factor of 40 is a perfect 4th power. That's huge. Right, that's what we're actually looking for, right? When we're asked for when we're saying the 4th root of 40. And because we can't find one, right? Because no perfect 4th power goes into 40 evenly, that means that this 4th root of 40 is already simplified. There's nothing to do. So this was kind of a trick question. Right? There's nothing to do. There's no way I can break this apart, because there is no perfect 4th power that goes into 40 evenly. And if you want to see that even further, let's start writing some of the perfect 4th powers. Again, 0 I'm not going to do. 1, again, 1 is a perfect, it doesn't matter, right? 1 goes into everything. 2 to the 4th is 16. I guess I should have switched that, right? 16 doesn't go into 40 evenly. 3 to the 4th, is 81, and that's too big, and so you can right away see that, again, no factor of 40 is a perfect 4th power. So that is already simplified. I don't have to do anything else. I just leave it as the 4th root of 40. Done. All right. Okay. And then my last two examples are dealing with some fractions. You have a numerator and denominator where part of the fraction it has a radical in it. And we're asked to, in both of these last two examples, we're asked to simplify the expression. Now it is a fraction, right? So when you're asked to simplify a fraction, remember what that means. That means that the numerator and denominator can't have a common factor. All right. So first I'll simplify the radical. Let's do this off to the side. There is a radical in this, right? The numerator, over the big bar, is this 6 plus the square root of 45, right? A radical. Divided by, and then the denominator is simply 3. So first I'll simplify the radical, and then we'll simplify the fraction, right, as a whole. So the square root of 45. Alright, so 45 is not that large, right? And hopefully, this is a square root, so we are looking for perfect squares that go into 45 evenly. So you can do the thing where you break down 45 to completely, it's actually 3 squared times 5, right? That's the square root of 3 squared times 5, right? 3 times 3 times 5, or just say that's 9, right? The square root of 9 times 5. And then you use that product property, break this up. This is the square root of 3 squared, or the square root of 9 times the square root of 5. They have the perfect square here, the non-perfect square here. And the square root of 3 squared is, again, technically the absolute value of 3, because it's an even root of an nth power. But what is the absolute value of 3? It's just 3, right? So it's 3 times the square root of 5. All right. So I simplify the radical. Let's write that in here now. So this fraction, the numerator, is 6 plus, then the square root of 45, right, simplifies to 3 times the square root of 5. All right. And then the denominator is just 3. All right. Now I have to warn you. Here's a little, I'll put this on a separate page actually. So here's a little warning for you. Don't do the following. Too often I see this happen. 6 plus 3 times the square root of 5 like this. And people will put the 6 and the 3 together. Oh, 6 plus 3 is 9. So this is 9 times the square root of 5. This is wrong. This is incorrect. Reason being is you got to think of your order of operations, people. Right? You got to think of the order of operations. Remember, you do multiplication first and then addition. So you would multiply the 3 and the square root of 5 first and then add 6. So you're not adding 6 to the 3, you're adding 6 to the 3 times the square root of 5. That totally means something totally different. Additionally, let's actually punch these in a calculator and see what values we're getting. And I'll put a little wavy equal, approximately equals. If I punch these numbers in a calculator, here's 6 plus 3 times the square root of 5, right, the left side. That's, approximately 12.7. All right, let's say approximately 12.7, just to one decimal place. The other side, if you decided to add the 6 and the 3 and say, 9 root 5, 9 times the square root of 5. See, that's approximately 20.1 if you go to one decimal place. Definitely not the same. They are not equal. All right, so be aware of the order of operations. What would get done first? Not the 6 plus 3 part. What would get done first is the 3 times the square root of 5 part. All right, so don't add before you multiply. All right, so now that I've warned you about that, again, I see that happen way too often. After I simplify the radical, well, this is a fraction. All right, so let's now simplify the fraction. All right. So remember how to do that. You factor the numerator and denominator. I've done a video on this in the past, so I'm not going to go over all that again, but yeah, I'll just say it. You factor the numerator and denominator completely, and then you divide out any common factors, get rid of any, cancel, I guess you could say, any common factors that the numerator and denominator have. So what I'm doing here is factoring the numerator and denominator. It says factoring, sorry, it's kind of too tiny there. Well, too blobby. Alright, so look at the numerator. There are two terms. There's 6, and then there's this term, remember terms are products separated by plus signs. There's 6 times 1. This is 3 times the square root of 5. There are two terms. And what's a common factor, right? We can break down 6 to 3 times 2, right? 6 plus 3 times the square root of 5, right? When I look at all the terms and break all the terms down completely, 6 is 3 times 2, plus, and then the second term is just 3 times the square root of 5. And you see how they have this common factor of 3, right? So I'm reversing the distributive property, factoring out a 3. So if I do that, factor out a 3, you'd have 3 times the quantity. Then when you remove a factor of 3, what would be left over? The quantity 2 plus the square root of 5. Alright, and again, that's in parentheses because that's what happens when you reverse the distributive property when you factor something out. You have one factor of 3, and then this whole thing in parentheses, 2 plus the square root of 5, that's the second factor. There are two factors in the numerator. Alright, and then the denominator, well, 3 is already prime. 3, I guess you could write as 3 times 1, but it doesn't break down any further. Okay, and then you have some common factors. Hopefully it's easy to see that the numerator has a factor of 3, the denominator has a factor of 3. Those divide out to become 1 technically, right? 3 divided by 3 is 1. And so all I'm left with when I'm all said and done simplifying this fraction, the 3's are gone, and I have 2 plus the square root of 5 in the numerator, which since it's the only factor left, I don't need parentheses around it, and 1 in the denominator. Now there's no reason to write divided by 1, right? That doesn't do anything. So there you go. This would be considered as simple as that fraction would get, right? After simplifying the radical, of course, that's what the video is titled, right? And then afterwards, simplifying the fraction. And just, of course, I like to, you know me, I like to double check. I'll punch these in the calculator and see if they're actually the same number. So here's what we started with. So the numerator has, two terms, multiple terms in it. I'm going to put that in parentheses, right? That whole thing is the numerator. So in parentheses, 6 plus the square root of 45, right? And then close parentheses. That's the whole numerator. Divided by, and then, the denominator just has this one term of 3. Alright, so that's 4.236067977, blah, 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 right? 4.23, 4.236, okay. How about this 2 plus the square root of 5? Well, hopefully they're the same. They better be. That's what I'm saying here. All right, 2 plus the square root of 5 is indeed the same number. Wonderful. And please do that on your own as well. When you're working on stuff like this, please always double check your answers. Is this statement a true statement? Is this expression truly equal to this other expression? All right, so I've got just one more of these. So it's very similar. All right, my numerator has the two terms, -2 plus, and then a radical, the square root of 32. The denominator has the one term of 4. All right, so I'll simplify the radical first. So off to the side, here's the radical. That's the square root of 32. All right, when you break down 32 completely, it's the square root of 2 to the 5th power. 2 to the 5th power. Now let's talk about 2 to the 5th. That power, this is a square root. The index is 2. The power is definitely 2 or greater. In fact, it's 3 greater than 2. Pardon me. So when I do that thing where we break it up into a perfect square times a non-perfect square, the index is 2. That's definitely 2 or greater, this power of 5. We just need to find the largest multiple of 2 that's less than 5, or less than or equal to 5. Let's say less than 5. What's the largest multiple of 2 less than 5? Well, there's 2, then 4, then 6 is too big, so it's 4. So I can break this up into 2 to the 4th power times 2 to the 1st power, right? This would be 2 to the 5th, right? Remember, when you multiply two things with the same base, you would add the exponents. That's 4 plus 1. So I have it broken up now into my perfect square, right? Remember, anything to an even power is a perfect square, a perfect second power. And then not, right? 2 to the 1st would not be a perfect square. And in fact, we've seen this already. What is 2 to the 4th? It's 16, right? So if you want to think of it this way as well, you can think of 32 as 16 times 2. So when I'm done simplifying this radical, right, coming down here now, the square root of 32, I can break up into the square root of 16 times the square root of 2, or the square root of 2 to the 4th times the square root of 2. And what is the square root of 16? The non-negative square root of 16, that's 4, times the square root of 2. And again, if you want to double check, punch in the square root of 32, and then punch in 4 times the square root of 2, and indeed they are the same number. All right. So I'm going to use this now. Go back to our fraction. The numerator is now this, negative 2 plus, and then the square root of 32 is this, 4 times the square root of 2, all of that divided by 4, and then we do the simplifying of the numerator and denominator. All right. Look at the numerator, it has 2 terms. There's 2, negative 2, but that's like negative 1 times 2. So that has a factor of 2. And then the second term has a factor of 4, which is, 2 times 2. So this also has a factor of 2. So these both have a factor of 2. So I'm going to factor that out, 2. And when I remove a factor of 2 from these, what's left in the first term would be the negative 1. Plus, and if I remove a factor of 2, this is 2 times 2, times the square root of 2. If I remove a factor of 2, what's left is 2 times the square root of 2. And then all this, there's 2, so there's 2 factors in the numerator. This 2, and this stay in parentheses here, negative 1 plus 2 times the square root of 2. And in the denominator I have a 4, which is, 2 times 2 again. So hopefully you can see that, this factor of 2 in the numerator becomes 1, and, takes away one of the factors of 2 down here, right? 2 goes into 4 twice. So I'd be left with a factor of 2 down here in the denominator. Okay, so the simplified fraction is negative 1 plus 2 times the square root of 2 in the numerator, all of that divided by, and then just 2 in the denominator. And this is great. All right, this is totally simplified now, right? The numerator and denominator of this fraction don't have a common factor anymore. But you could also write this, right? You could also say this, the numerator has multiple terms, and remember adding and subtracting fractions. This is just like if I were to add 2 fractions with a denominator of 2. So you could split this up where you take each term in the numerator divided by 2. This negative 1 plus 2 root 2 all over 2 is the same as negative 1 over 2, right, the first fraction, plus, and then that other term in the numerator, 2 times the square root of 2 divided by 2. All right. Remember, this is just adding fractions but reversing it. All right, because if I were to add these two, right, remember you keep the common denominator and then just put the numerators together, you get this thing in the box over here. And then we can simplify this second fraction over here if you'd like. negative 1 over 2, that's simple already. There's no common factor in that numerator and denominator. But this second fraction, there's a common factor of 2, right? There's 2 times the square root of 2 in the numerator. There's just 2 in the denominator. So those divide out to be 1. And I'm left with, negative 1/2, that first fraction, plus, and then when you divide out the 2's, all you're left with is the square root of 2 divided by 1, or just the square root of 2 as a second fraction. And very often in textbooks you'll see it written out this way. But this in this box on the left, this in this box on the right are indeed the same number, and I'm going to show you that right now. So either way, either one is fine though. All right, so let's see. Clear this out. Let's put in the original expression. So in parentheses, I've got the numerator, negative 2 plus the square root of 32. And then I close the parentheses. That was all the numerator. Then divided by 4. Okay, and I've got this number of 0.91421355624 and so on, some crazy decimal. All right, now we went through and simplified the radical and then simplified the fraction and got down to this here. Let me punch this in, this single fraction. So again, the numerator has multiple terms, so I'm going to put in parentheses. In parentheses, I have negative 1 plus, and then 2 times the square root of 2. That's all in the numerator. Divided by, and then the denominator has just the number 2 in it. And look at this, it's the same number, 0.91421355624. Wonderful. Or if you wanted, divided each term in the numerator by 2. Right, like I did here, and then canceled the 2's and all that, simplified both fractions like this when they were split up. I have negative 1/2, so negative 1 over 2. All right, there's negative 1/2, and then after that, plus the square root of 2. And you will see, indeed, it's the same number, 0.914, so on. Wonderful. Okay, so lots of stuff to remember here. Right, there's that product property for radicals. Remember that as a property of real numbers only. So the the nth root of a and the nth root of b need to be real numbers in order for you to put them together, make it the nth root of ab, and vice versa. If you want to split up the nth root of ab, the nth root of a times the nth root of b, you have to be sure that a and nth root of a and nth root of b are real numbers. Okay. And you're looking for, you got to pay attention to the radical. You got to pay attention, is it a square root? Then you're looking for perfect squares, powers that are multiples of 2. Is it a perfect cube root? When you see a cube root, right, obviously you're looking for, perfect cubes that are factors, and fourth roots, perfect fourth powers, etc. Yeah, so just a lot to keep track of, unfortunately, I know. But with practice, you'll get better, just like with anything, any skill. As I like to say at the end of these videos, do the best you can to learn the material on your own before you go looking for help. So I have found that people who put in the time and the effort to learn something on their own, they tend to remember it better and for longer. So read the material, of course. Read the author's examples, perhaps even try to work out the solutions to some of the author's examples before you see how the author did it themselves. And compare your work with the author's and see if you can learn from some mistakes there. Obviously, work on loads of exercises, tons of practice problems, to hone your skill. And check for solutions to those if they're made available, so you can check yourself and keep track of your progress. And don't just give up after the first attempt at a problem. First approach, very often in mathematics anyway, there are several approaches that'll work for any particular problem. So if after several approaches at a problem, several different tries, and you're still not getting it, well, perhaps you should read the material one more time. Maybe even a third time, more slowly, more deliberately. Take good notes. Because if you've been working on problems too, there's a good chance you have a better idea as to what the author wants from you, what the author's asking of you. So then you'll know better what to look for on the second or third read-through of the material. And perhaps you'll see some things too that you didn't see the first time that'll shine some light on the subject, make it make more sense, and make the problems that much easier. But if after that, if after several read-throughs of the material and several attempts at problems, still not making sense, still not getting it, then it's not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's loads of those too. Videos like this one, or plenty of other ones out there that are better than mine. I assure you they're out there and they're easy to find. But just keep at it is all I'm saying. Stay persistent. Keep practicing. Don't give up. I think the hardest part is to try to have a positive attitude about the subject that you're learning. That is definitely easier said than done, but if you have a belief system where I believe I can do this, I know I can, I'm going to have a good time doing it, have fun, maybe even maybe even have fun doing it, have a positive attitude about it, an open mind about it, you'd be amazed at the difference a little change in mindset can make, a little change in attitude can make in the learning experience. So stay persistent, keep practicing, stay positive, and don't give up. And I just know you'll get it. Thank you very much for watching.